Hello, I'm Riccardo Annibali, and I am one of the co-authors who participated to the development of this research project. Firstly, I'd like to thank Professor Camomilla for believing me and for letting me to partake this Congress. The title of our work is Biomedical Investigation of KIZAMI TSUKI in Karate Athletes, and in this presentation I'll talk about what we have found out during this investigation. The purpose of our work is to find out kinematics and kinetics characteristics of this punch technique and investigating the contribution of conditional, technical, and coordinative factors to the proficient performance of KIZAMI TSUKI. This presentation will be subdivided in four main pillars: introduction to better understand what KIZAMI TSUKI is, and if someone already analyzed this task; methods, in which I'll explain some details about the modus operandi of this research; results, score analysis, and some considerations about technical and coordinating factors; and at last the discussion and conclusions. So, what is KIZAMI TSUKI? Punching action represents the most frequently performed attacking techniques in karate combat competitions, representing almost 75% of the total action performed. In this framework, we find the KIZAMI TSUKI, one of the most common punching techniques. And how is it performed? KIZAMI consists of a forward punch performed with the feet on the same side as the forward leg facing the target, as we see in the video. This technique is analog to the jab of boxer, but its impact is comparable with the facing lunge, where all the body momentum is used to transfer speed to the fist. To be awarded points in karate combat competition, a punch has to be performed with the proper technique at maximal speed, without hitting the opponent forcefully. Punches require coordinated action of arm, trunk, and leg muscle groups. Lower limb position and the torque generated at both lower limbs are crucial in determining the final punch force. Leg drive has been observed to build up momentum in the kinematic chain. On the other hand, the movement of the trunk in this type of karate punch has a limited role in punch force development, and it needs a proper stance. Forearm extension reaches the greater peak angular speed, and then the arm flexion suggesting some speed transfer from the proximal limb to the distal during movement. Scientific knowledge on these actions in karate is only at the early stage. Previously, it was shown that in karate there are positive correlations between the lower limb maximum power and punching kinematics, both for single action or combination of punching techniques. On the other hand, the vast majority of these studies about punching techniques is focused on boxing. The contribution of lower limb to punching force in novice boxers is approximately 38%, with the trunk rotation contributing almost equally. This contribution varies according to the technical level of the performer. However, lower limb kinetics was not very much correlated with the peak result fist velocity during the rear hand punch in amateur boxers. The use of CRP, already investigated in previous studies, has been claimed to be an essential tool to better understand the role of the articular muscles when investigating the motor control of multi-joint actions. In this slide, we can see how CRP could be interpreted. A greater phase angle of one joint with respect to another should be interpreted as a lower movement, or smaller movement amplitude of the joint analysis, or a combination of both. To this aim, the correlation between the punch velocity, considered as a performance measure, and general and frictional power, upper and lower limb kinematics, and the upper and lower limb coordination was investigated. Now, let's talk about the methods. Moreover, here there are some details about the athletes, such as body mass, age, and so on. Also, all participants were athletes competing at the national level, with at least 15 years of karate experience. Participants were asked to perform 6 repetitions of KIZAMI TSUKI punching technique against a handheld target at their maximal speed. A 7-camera motion capture and 3 force platforms were used to obtain full body kinematics. A UWA protocol was used to derive ISBS convention joint kinematics values. To investigate the coordination between the propulsive action of lower limb and upper limb punching movement, knee and elbow flexor extension kinematics during a punching phase were used to create a phase plot. For any point of each phase plot, the phase angle phi was computed as the inverse tangent of the ratio between the normalized angular velocity and the angular displacement. The continued relative phase is the difference between the phase angle of knee segment and that of the elbow segment. For each CRP curve, the mean value was computed and used for further analysis. These are all parameters correlated with the wrist velocity. Lower limb power was obtained as byproduct of the GRF and the center of mass velocity. The frictional power is obtained from the combination of horizontal components. Center of wrist velocity, elbow, and knee flex extension were obtained from the mechanical model using the joint coordinate systems defined as in ISBS standards. Descriptive statistics was performed as the mean standard deviation after testing for normal distribution using Shapiro-Wilk test. To investigate the relationship between maximum wrist velocity and other performance parameters, a three-step analysis was carried out. A linear correlation of each variable with the peak of wrist velocity. A multiple linear regression analysis on all variables non-mutually correlated to identify predictor contributing to the maximum of wrist velocity, and a multiple linear regression of predictors with the peak of wrist velocity. For all statistical steps, alpha was set to 0.05. In the next slides, we'll talk about the results achieved during this study. In this plot, the paradigmatic behavior of two athletes is reported. These athletes have the similar behavior. They differ in the presence or absence of knee flexion before an elbow extension. Therefore, CRP permits to show different strategies for punching techniques. The linear correlation of each variable with the wrist velocity is plotted here for significant correlations. Descriptive statistics is given for the other variables. In general, analyzing the single correlation between the independent variables and the performance parameter, it's emerged that elbow flexion has the higher correlation. But also knee flexion and CRP are good parameters to predict wrist velocity. When performing a multiple linear regression analysis using all variables to predict wrist velocity, elbow max flexion, CRP, the time delay between peak friction power and the wrist velocity, and the max net power were the significant predictors of wrist velocity. And now, the last part. The study aim was to investigate kinetics and kinematics features of this technique, and it was find out CRP values clearly depict a role for knee and elbow coordination as a determinant of performance. Moreover, it was discovered that the elbow peak flexion was the best single predictor of punch velocity, as already said. The peak net power with the power vertical component predominant over the horizontal one was one predictor in the optimized multifactorial model. And finally, the horizontal generated power was not directly correlated with the wrist velocity. Summing up, KIZAMI TSUKI is a very versatile technique with a wide gamma of uses going from various combinations to single strike situations. This study highlights the predominant role of lower limbs net power generation and elbow flexion per load of wrist velocity. Knowledge of these determinants of punching performances could orient training programs and consequently help enhancing punching performance. I acknowledge the ICOS project supported by the European Union under the Erasmus Plus program to support the research, and I thank you for the attention.